All right. The other thing comes back to, do I think FinFETs are going to take over the market in 2 years? All right. So if you read the stuff by TSMC and Global and Samsung, they're all coming out with a FinFET by the end of 2014. Personally, I don't think it's going to happen. I think they will have a FinFET. I just don't think they're going to have it by 2014. And the reason is, if you have a look at what you must have, these are not optional. You have to have this to make a FinFET, at least if you're going to copy Intel, which they all do. None of them are going to go invent their own ways of doing it. Is you have to have true gate last. Okay, you can't do the FinFET with gate first, very tricky. Then if you think about a fin, right, you have to have epi source drains on both the NMOS and the PMOS. And the reason for this, it goes back to how do you get current out of the device. It's an R external argument, right? So if you think about a fin as a hose pipe, okay? You can't, at some point in time, you cannot get more water through that hose pipe. The only way to get more water through the hose pipe is to open up the end, okay? And then you can pump more water through. And that's exactly what the epi source drains do on the fin. So when you see the picture of an Intel fin, you see this little fin and this gate, then you see this big ball on both sides of the gate. That's the epi source drain. You need that on both NMOS and PMOS. You need ALD gate work function metals. You need self-aligned rectangular borderless contacts. So what this is usually with old process, what you'd do is you would sell aside, and then you'd come back later and you'd put in a hole, a little square hole, and you'd basically fill it up with basically metal, and you'd contact the device. Well, what you need now is you need what's known as trench contacts. So trench contacts, you don't just have a hole down, they basically extend the entire gate length. But even more than that, you actually need to do the contacting, the cell-assidation through that trench. Now, when you think about why it is, if you had a micron long device and you were off by a little bit in where you did your salicide or where you plugged the hole, you're still contacting the device, okay? But when you've got a 10 nanometer fin, your contact better be on top of that fin, otherwise you're in trouble. These are not easy technologies. Now, if you have a look, Intel's had these technologies for a while, but none of the major foundries have these technologies. They have maybe one or two of them, like gate last, the gate last, now, you know, TSMC has that now. But a lot of them don't have all these capabilities. And if you look at Intel, they were on their 5th generation with SIGI source drain integration. They were on their 3rd high-K node. Most of these guys are on their 2nd high-K node, and if you look at companies like Samsung, they're on their 1st gate last node, right? And there's a lot of learning that comes along with this. Intel basically had 2 NMOS ray source drains EPIs. You know, they introduced it in 32, and they took that knowledge and they put it onto the FinFET at 22. The foundries don't have that. So this is a lot of information. There's a lot of learning at Intel that went into making the FinFET work. And if you have a look at the foundries, they really don't have all this knowledge. So for them to replicate all this technology in one node is going to be extremely challenging. The other thing is, it's questionable whether the FinFET actually scales below 14 nanometers. So Intel claims it does. I've personally done studies while I was there which showed that in order to scale it to 14, you'd probably have to move on to FinFET on SOI type technologies. And when you think about how Intel does the FinFET now, you got your fin, but then underneath the fin, there's nothing, right? So what happens is you basically got a BJT underneath the fin. So if you want to keep scaling, eventually what happens, your leakage path is underneath the fin. So all that work you did in basically building this fin, you've kind of thrown it away because you've got this leakage path underneath the fin. If you go to fins on SOI, that raises a whole bunch of other issues, which is, for instance, how do you grow a good epi on a fin when you don't have the underlying silicon to basically grow it on, right? Because it has to seed off something. And you must remember that when you're doing the fin, you actually etch away the fin because you need to get the SIGI in there to stress it, right? So when you grow the epi on the fin, it's basically seeding off a very small amount of silicon at your oxide level. So if the whole thing is SOI, you're out of luck. And then the other thing is, you know, the thing where it really becomes tricky is the true cost of developing is very difficult. So you can go have a look at basically an Intel 10K. I'll come to you in a sec. And you can see that basically the capex increased $2 billion over the time when they were developing the FinFET. And again here, I'm going to come back to that point where I said to you, Intel doesn't sell wafers. Intel sells parts. This is the main difference between a foundry and an IDM. So when Intel makes a wafer, they're selling that wafer for 200 to 400 or whatever thousands of dollars. When you're TSMC, you're selling that same wafer for $6,000. So you can imagine who has to pinch their pennies more. So, okay, so if you have a look at where the foundry is right now, right, most of them have just released their 28 nanometer device, right? And if you read the press, nobody's really happy. TSMC's got horrible yield. Right now, the foundries are selling every piece of 28 silicon they can run. So there's a huge demand for it. Now, at 20, they don't like what they see. Because what happens when you scale from 28 to 20, the rooms run out, right? So as I showed in the graph, all your TOCs, even with high K, off the table, you used it all at 28. Your stress, you used it all at 28. So when they look at what's happening at 20, they don't really like what they're seeing, right? So they have to keep up, right? It's this whole ecosystem. All right, it's basically if there's money to be made somewhere, somebody's going to try and make that money. So if you're a Qualcomm or Apple, you're sitting there going, well, if I don't do something about this, what happens if Intel comes into the mobile market, right? You can't, if you're in a competitive study, you can't let them open the door. So they go to TSMC, and TSMC is in the same boat, because if Intel starts to win, and Qualcomm disappears, and and all these companies start taking hit, eventually it hurts their bottom line too. So basically there's a race for them to come up with a technology which is competitive with Intel's technology. And it doesn't happen overnight. So what they're actually doing, it's kind of interesting, is that they're all coming up, it's a very interesting time in the industry now, because they're all coming up with their own special blend of transistors. So, for instance, TSMC announced their 60 nanometer technology, which has a 20 nanometer back end with a 16 nanometer front end. So they're not changing the metal pitch. Okay, and then Global Foundries announced essentially the exact same thing, but they're calling it a 40 nanometer technology. So the bottom line is here is that the numbers that you put on the technology, 28, 20, it doesn't mean anything anymore, right? At one stage, it used to mean it was the smallest feature in that technology. There's nothing 28 nanometers on anything these days, right? It doesn't mean anything. So what's happening is the industry is kind of trying to find a way to basically continue scaling, continue competing with Intel. They don't want Intel to take over. And there's a lot of money to be made. Qualcomm literally cannot make enough parts. The demand for Qualcomm parts right now is greater than what they can actually produce. So whenever you have that type of situation, you're going to drive towards having this good technology. And the thing is, think about the time involved here. Okay. So if you're talking about an advanced design, I'm not talking about some simple Bluetooth chip. I'm talking about like a Qualcomm Snapdragon. The design cost for Qualcomm are about $150 million. They start doing that design at about the same time that TSMC releases their first design kit, which is about 6 months to a year after they start doing the technology. It takes them about 2 years to do that design, right? So basically, if you think about the industry, you need a lot of things to come together in order to have success. You need the technology to be ready, you need the product to be ready, and before they've even sold a single part, these companies have spent hundreds of millions of dollars. So, why do they start now? They have to. The market, why don't we just stop and go, okay, my phone's good enough, I don't need any more. It's just, there's money to be made, and the market's going to drive down that. So true gate loss stack is, so there's different high-K metal gate stacks, right? So there's the IBM way, which is gate first, right? So you put everything down, you drive lanthanum through the thing, and blah, 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 and you'll end up with a mid-gap work function, right? Then there is what Intel did at the 45 technology, which is dielectric first, gate last. So what they do is they first put down the high K, and at the end they come scoop it out, and then they put the metal gate down. The true gate last is when everything goes on at the end. The high K and the metal gate get deposited at the end. So it's just basically, the way to think about it is that the last thing you do on the front end in true gate last is you put down the high K and the middle gate. You with me? You with me? Okay. You can come ask me if I can draw it on the board. It's pretty.
Just one quick question. You mentioned that FinFET is not likely to be scaled below 14 nanometer.
Yeah.
But if you change to SOA, where do you think it would be further?
There's a lot of challenges there too, right? So when you go over to SOI, you know, all these things that you need, you know, it's not, so I'll give you an example here. Epi growth is not, as far as I'm concerned, it's not a science, it's an art. I mean that dead seriously. It's just a lot of tinkering around and figuring out the gas flows, and it just works. I've never spoken to an epi guy who can go, I'll nail that on the first shot. There really is, it really is an art form. So when you go to SOI, you're learning, you're going to lose 5-6 generations of knowing how to grow that epi. So let's just say you can get one more generation out of it. What other issues come along for the ride? And then when you go to, you know, and the interesting thing is, fins on SOI are kind of going back to the type of SOI structure they used for PD, not for FD. So they're going back to the thick oxide. So then you get other issues, which is, you know, how do you tap? How do you have ESD protection? So it might help with the scaling part because of the sub-fin leakage, but there's a whole bunch of other things that come into it, right? And that doesn't only affect the process technology, it also affects the design collateral, right? So you've got companies who have spent billions of dollars building libraries and IPs and you know, the IP libraries and all that stuff. And now you go change the technology and now you go, you can't have that anymore. So again, do I think it'll, you know, not scale below 14, maybe you get down to 10. Maybe I'm off by one node. But it's definitely, FinFET's definitely not like the end game, oh, for the next 30 years we're taken care of. We're going to need some form of massive innovation in the next, my guess is 10 years. Okay, so again here, what I just want to point out, I'll go over this quickly, is if you look at an SOC technology offering, what they call the library or whatever the case may be, depending on the foundry, really what you have is you have multiple, sometimes up to 5 VT devices, multiple supply voltages, right? Because for an SOC, you're going to have your logic and you're going to have your I/O, right? You're going to have some analog on there. So you need different supply voltages. You're going to have different oxide thicknesses. You know, your I/O device is always going to be thicker oxide with higher voltage. And the thing is, coming back, I've already kind of discussed this, but when you've got a Tri-Gate or a FinFET, how do you actually change the VTs, right? So people go, oh, you grow the fin taller. Well, you can't really do that, right? Because you basically, you know, you get to pattern these things once. You know, when a fin's 10 nanometers, you can't keep hitting it with cleans and etches. You're going to just have no fin left, right? Well, make it wider. Well, you can't make it wider because of the cost of basically lithography, right? So that's why these things are nicely ordered, right? Because if you go, I want one fin here and one fin there, the patterning of these things becomes extremely hard. And the other thing is the etch rates. The reason why you want everything uniform is because that way you can control your etch rates. If you don't have uniform gaps, the fins which are further apart are going to etch a lot quicker than the ones that are closer together. So you can't really change the VTs that way. So really, the only way you can do it is by having different work functions and by having different lengths. So it's not very it's not a very agile technology, let's put it that way. So the SOC guys are going to have a lot of trouble with this. And again, you can kind of see that if you have a look at Intel right now, if you have a look at their actual, and this is actually the perfect slide for it, if you have a look at their device numbers, they're fantastic. I mean, I can't sit here and tell you, oh, I've seen better. They are fantastic. The problem is that if you have a look at the product level gains, they don't add up, right? So if I'm saying I've got 40% more drive current, which is what Intel claims, why don't I have 40% more perform? You know, why am I not 40% faster? And the reason is not everything comes for free. So when you go to the FinFET architecture, what happens is you increase your drive current by 40%, but you also increase your parasitic capacitance by about 40% too. So if you're in a device like an Intel CPU, it's called back-end loaded, right? So the capacitance in the metal layers in the back end is so much greater than the capacitance of the device that that's really going to dominate the capacitance of the system, so you're fine. But if you're an SOC device, your front-end capacitance is a lot more important. So this is not going to perform that well for an SoC device. And you can actually see that if you compare the technology offerings from Intel versus, let's say, Samsung or TSMC, what Intel will do is they will basically they'll plot the capacitance versus performance, and they pick the point where it's just optimized. You get the most capacitance, but you get the most, it's where you get at some point in time your drive will level out. So they run it at the highest possible capacitance where they don't have any drive penalty. If you have a look at the foundries, they often give up significant drive current to lower that capacitance because that's what the products that are being built on their technologies require. So, so there are issues. So the question here is, and I think I get into the whole variability thing, but there's variability issues with FinFETs. Again, if you saw the ChipWorks report on the Intel Fin, right, you don't have these perfect, 10 nanometers wide, 20 nanometers high, these perfect, chess-like pieces. You have these fins which are all slightly different shaped, and they're triangular, and some of them are rounded, some of them are pointed, and that gives rise to VT variation. So that's why the Intel parts that are coming out right now on the FinFETs are not going to be running at 0.7 like they show in the device papers. They're going to be running at 0.95, 0.9, no different than a planar technology because of the added variation. So the question here is the investment in FinFET justifiable? Now, if you're Intel, hell yeah. I'm not going to argue that. It's a great technology for them. But if you're a foundry and you serve, and you basically serve as, you're serving companies like Qualcomm and Broadcom and places like that, it really remains to be seen. I'm not saying no. I'm saying it remains to be seen. All right, so there's a couple of other things here about the actual FinFET. Because of how you make them, you have to have a lot of dummy gates in order to have this uniformity for etching, and that actually takes up a lot of space on the die, so that's cost. And I've gone, this is the variability, when you have a fin, there's a lot of additional sources of variation of the structure that you didn't have in a planar device. And you can see that in basically the published paper here, where you see the variation the most is not going to be in the drive current, it's going to be in the leakage current, right? Because that's exponentially dependent on VT. So you can see over here, there's a massive variation, almost, not quite 4, but more than 3 orders of magnitude. So that's not good. If you're a designer, that makes life extremely difficult. The other thing is, again here, when people think about this FinFET, they think about this classic textbook FinFET where everything's nice and square. And it's not like that. And really what you have is you've got 3 devices in one. So you've got this top device, which is perfectly confined with the wraparound. Then you've got this middle device, which is kind of, this double gate device. You've got this bottom device, which is more like a BJT than it is like anything else, right? Because you just got NPN and there's no gate. So it becomes very difficult to basically optimize this architecture. And it's not that it can't be done, but again, to optimize this costs money. Okay, so basically the summary on FinFET is it's a very impressive technology. I think Intel's way ahead on not just the FinFET technology, but all the aspects that go into the FinFET, into the Fin technology. The EPIs, the metal gates, the contacting schemes, the self-aligned contacts, they're far ahead. So the drive current and the short channel effect's fantastic, but the parasitic capacitance is really poor. Variability is very poor. I think that's going to be a big challenge for Intel going on. I think if they want an SoC technology that really is competitive, they're going to have to work on the variation. Even if it comes at the cost of some drive current, it will be a positive trade-off for them. And then the other thing is it's probably good for GPUs. GPUs are slightly different than CPUs is because density is everything. I don't know if you guys know this, but GPU clock frequencies have hardly changed over the last 5-6 years. It's not like a CPU where you keep bumping up the clock frequency. With GPUs, it's pure parallelization. You just basically, the more cores you can have, the better you are. So again, my summary there is great for an IDM. It remains to be seen how it works in Fab Light.